from plasma physics, right? And we have chemists and we have engineers, we have people who come from applications, and we need each other to understand all aspects of ALD. So we've seen that today and yesterday as well. But now, my time.
Yeah. Well, thank you, Julien. And well, first of all, I would like to thank your organizers, ATLANT and Maxime, especially also for inviting me here. I very much appreciate it to be able to see the premises here. And indeed, my background is also in plasma physics. So I will talk about some innovations in plasma processing for nanoscale fabrication. That's probably not a surprise. And time is short, so let's see whether this addresses. Nothing has happening so far. Okay, there we go. So what I decided to do is actually give you a quick update on several methods, all related with plasma, all related to plasma. So I'll first give you a very quick update on the status of plasma-enhanced ALD. Then I will say something about plasma-enhanced spatial ALD, then plasma-enhanced area-selective ALD, and then I'll come to the last thing that is, I think, also a very nice connection with the work of ATLANT 3D, is patterning by atmospheric microplasma printer ALD. Okay, so well. I don't think I really have to introduce the method of plasma-enhanced ALD. It's very similar to thermal ALD, but the big difference is that in the co-reactant step, you use a plasma. So instead of water or ammonia or whatever, you expose the surface to a plasma, which can be hydrogen plasma, nitrogen plasma, oxygen plasma, or many other possibilities. And this method is actually now very important. If you look at the number of papers or publications per year published, then you see on this plot here, you see that it's about 10% of the overall number of papers published on ALD. So 10% is not that much, although it's still significant. But if you talk to people in industry, then you learn quickly that more than 30% of the applications, 30% of the tools, I should say, because that's a little bit easier to quantify, more than 30% of the tools in industry are plasma-enhanced ALD. So from an industrial point of view, the plasma-enhanced ALD is very important. And that is related to several factors, working at low temperatures, throughput, other materials that you cannot easily make with thermal ALD. That is actually, these are some of the drivers to use plasma-enhanced ALD in industry. Now, I think I have to get started here. So we have been working on plasma-enhanced ALD for a long time, and we were looking into the role of ions during plasma-enhanced ALD, and we made an animation because I think we can classify or categorize the role of ions in several cases. So here, first of all, in this animation, we introduced the ALD cycle, the plasma-enhanced ALD cycle, and then there are basically four flavors. First of all, we can take the conditions such that we have mostly radicals during the plasma step and virtually no ions. And that would be very soft conditions. For some applications, this would be very important. Under regular conditions, you would have low energy ions, and they are more important than we thought initially because they can enhance surface reactions. And that is also very helpful in some cases. What we also have been working on, and we'll show that next, is that we can also increase the ion energy, and then we can actually modify the material. And this is something new, or relatively new, and that's interesting. But of course, we can also go too high ion energies, and then we get damage. So that's also where we want to stay away from, of course. And well, we have been working on this. You can read the blog that also with this blog site where you find much more information. But I would like to show you some work that we have been doing in the last, well, actually 10 years. We started already with this. So we have been working on controlling the ion energy during the plasma-enhanced ALD cycle. And what we have done is we have, this is the plasma ALD system that we use in this for this particular work. And we have been connecting the substrate holder with to a power supply. And the first one that we did is an RF waveform. So we apply an RF waveform to the substrate holder. We call that substrate biasing. And then you can see that for different conditions, we can increase the ion energy. So if you put a little bit of power here, then we can go from, what is it, 25 eV to over 75 eV, and here even up to 200 eV. So that's the first thing that we did. Now, very recently, we also have been implementing a new method, which is the tailored waveform. So that's shown here. And that is actually giving us even a more precise ion energy control. So it's precise ion energy, but also a very narrow ion energy distribution. So that's what we are working on right now. And we are really investigating what can we do, what is the role of the ions during ALD. And I will show you just one paper that we recently published to bring you up to speed. This is some work that we did on quantum applications, because also ALD is important for quantum technology applications. And what we were interested here is actually to make the superconducting material that is used in qubits, but also in resonators and true silicon vias, and also in single photon detectors. You need very high quality superconducting material. And the common methods right now in the lab, they are not scalable, so people are looking into ALD. And what we found out is that we can make high quality tantalum carbon nitride films, ultra thin, superconducting by plasma enhanced ALD using ion energy control. And the process, okay, slide doesn't want to, oh, the battery is running low, it says here. Anyway, I'll try to continue. If that doesn't really want to.
I think your mouse is.
Okay, now, okay, this is the, we'll keep going. So this is the process that we developed. This is the tantalum precursor. This is we use an argon hydrogen plasma. And for this particular case, we use RF biasing. And here you see the material properties where we vary the RF bias power here. And what we see is that especially the resistivity drops orders of magnitude here. And the material also gets more dense at a particular bias power. So that shows that the ions really have a very good influence on the material quality. We also check the superconducting properties of this material. If we apply no ion energy or a little bit of ion energy, then we don't get superconducting material. But here you see 20 watts of bias power, which is about 150 volts ions, electron volts ions. We get the best quality, we get the highest critical temperature, and this is actually the best material. If you go to too high ion energy, we probably have a little bit of damage. So this shows that the ions are very important for the material quality. Now, of course, ion energy control you can easily do if you work at low pressure. If you go to high pressure, that's a different thing. And then I'll come to the next thing, plasma enhanced spatial ALD. So first of all, spatial ALD, I think you are familiar with this. The difference is in temporal ALD, we have a static wafer and we dose the gases one by one. And over time, in spatial ALD, we have a static injection of the precursors, and then we move the wafer typically. So in both cases, the wafer sees the different cycles. Here is a function of time. Here is a function of the position, and of course also as a function of time, of course, in this particular case. So this is spatial ALD is very important now in industry, especially for throughput reasons. There are many applications of ALD in industry, and of course throughput is always very critical. So people try to solve that in different ways. People use batch reactors, but for plasma that would not be an easy solution. For example, ASM has a system where they have like multiple chambers to one robot, and then they have like 4 wafers per chamber that they can process. Other companies, they have been really going into spatial ALD, and basically they have a carousel where you put the wafers on, and then the wafers see the different reactants as a function of position, of course, because they rotate through these different zones. And this is used a lot in industry right now. This is plasma enhanced ALD, but it's at relatively low pressure still. So it's spatial ALD, but at relatively low pressure. One thing that we are interested in and that we have been worked a lot is what is the conformality? The conformality with plasma enhanced ALD, people were always asking questions about that, because one reason is that that when you have wall collisions, that radicals can recombine. So people were always wondering about this. Now we have shown that low pressure, that the conformality of materials can be good. It depends on the material, it depends on the plasma, but it can be very good. That's also proven by the applications because people are using it. Now the next question is, okay, how is it in spatial ALD, and how is it with plasma enhanced spatial ALD, and how is that atmospheric plasma spatial ALD? And that's something that we have been investigating. This is the tool that also Fred and Paul have worked with. This is the tool at TNO. This is basically a spatial ALD reactor, like the rotating system, as we saw before, slightly smaller. But this uses now an atmospheric plasma source. And this is a surface dielectric barrier discharge. And that's where we have been looking at the conformality of spatial plasma enhanced spatial ALD. The method that we have used is we have used the chips of chip matrix. These are lateral cavities where you can deposit the material in there, and of course the better conformality, the deeper the material go into these structures. And the nice thing is that you can easily do the analysis because you can take off the lid, and then you can easily measure the quality and the thickness of the film at the bottom. And I will just jump here to the results. So this was for silicon oxide and titanium oxide for atmospheric spatial plasma enhanced ALD. And it's a little bit difficult to see, but the longer that the exposure is, the deeper the material penetrates into the cavity. So here, this is the opening of the cavity here, and then this was inside the cavity. And the longer the plasma exposure time, the deeper the material goes. And here we have plotted the data slightly different by lopsometry, spectroscopy lopsometry. And what we can see is that for silicon oxide, we can easily get to an aspect ratio of 74. And for titanium oxide, even higher, more than 200, for a fairly short plasma exposure time, I would say. So that proves that also spatial ALD can be conformal, even plasma enhanced spatial ALD, and even atmospheric plasma enhanced spatial ALD. So I think that is a very important result that should stimulate maybe more the applications of this method. And we're even able to get some physical parameters out of this. This is the surface recombination probability for oxygen atoms, and we could extract these numbers. And what we found is that they are not very pressure dependent. So I think that's also very interesting to know, because that means that we can use these numbers pretty well with, in simulations for irrespective of the pressure that you use. Okay, so that was plasma enhanced spatial ALD. Now very brief about plasma enhanced area-selective ALD. Here the challenge is to deposit the material on a surface. But now, depending on the material at the surface, you want to have this material only on the growth area and not on the non-growth area. So depending on, so you have two materials. So this is the growth area. We would like to deposit material here, but not there. And here we did a lot of work to realize that. And this is a particular process for nitride, where we use inhibitor molecules, small inhibitor molecules, to block parts of the surface. So this we would block, and then the material could only grow on the blue material here, and then we do this cycle. The interesting thing here is that these inhibitor molecules, they are applied every cycle, but also removed every cycle, because we use the plasma here. So they remove the inhibitors. So that is also the nice thing with plasma enhanced ALD, that you can remove the inhibitors every cycle and you reapply them, so then you can keep the quality of the inhibitors high. The other thing that we did here, to make good quality material, we used this biosubstrate again. And I'll just show you here a result. This is low resistivity nitride with biasing, and we were able to grow this material now on the oxides. So here, these are the oxides, and we could prevent growth on the metals. So this has very interesting applications, especially in the semiconductor industry. This is another example, 2D materials. We were able to grow it we were able to grow it on silicon oxide and not on aluminum oxide. I think it's reversed there. So that is another example, and maybe that's a nice bridge to the next presentation.